Hi there, and welcome to this video on A-Level Chemistry for the AQA Specification, focusing on the topic of bonding, and in particular, on bonding and properties. Hi, I'm Manisha from StudyMind, where we help you to revise A-Level Chemistry with our helpful revision resources tailored to your subject, your specification, and to you. If you're new here, please make sure to click that subscribe button, and whilst you're watching, please leave any comments down below about anything you're unsure of. If it's your first time watching, make sure to let us know so we can send you our free revision resources. We also have helpful timestamps to guide you through the video. So, let's get started. Welcome to lesson 4 of 7 in this tutorial. Bonding and physical properties. This is the 4th lesson in our series of 7 videos on the topic of bonding. In the last lesson, we looked at metallic bonding in atoms and the term metallic structure. Here are the key learning objectives for this lesson. The first is to look at the structures of ionic compounds, and the next is to look at the structures of simple and giant covalent compounds. We'll then move on to the structures of metals and the states of substances. Here are the AQA specification points for this lesson. Feel free to pause the video now and have a quick read through them before we begin. We'll start off by looking at the 4 types of crystal structure. There are 4 main types of crystal structure you need to know about. These are ionic, metallic, giant covalent, and giant molecular. Ionic compounds will form crystals with a giant ionic lattice structure. Something you should bear in mind is that giant in this case does not mean that the structure is large. In this context, giant means it is indefinite to say exactly how many ions are present. A giant ionic lattice is a structure that has a regular arrangement. The reason that a giant ionic lattice has a regular arrangement is because the units or crystals it is made up of are exactly the same, or repeating. Some ionic compounds will form giant ionic lattices, however others will form slightly different shaped structures. Sodium chloride is an example of a cube-shaped ionic lattice. As shown here, it's important to note in this diagram the green dots are not chlorine ions, but chloride ions. The next specification point will look at the structure of a sodium chloride in more detail. This figure shows a representation of a giant ionic lattice. Here, we can see that the repeating basic units of sodium ions and chlorine ions will form a cube-shaped compound. Each of the lines represents an ionic bond between the ions. Here, we can see the ionic bonds are between the positive sodium ions and the negative chloride ions. Before we move on with this tutorial, there are 2 key definitions you need to understand. The first is for the word polar, and the second is for the word molten. A polar molecule is a molecule that has a partial negative charge and a partial positive charge. Here, we can see an example of water as a polar molecule. This is said to be electronegative. We will cover this in a later tutorial. A molten compound is when a compound is liquefied by heat. Now let's look at the melting point and conductivity of metals. The physical properties of an ionic compound are determined by its structure. For example, electrical conductivity, melting point, and boiling point. An ionic compound will have a very high melting and boiling point. A large amount of energy is needed to break the forces of attraction between the ions, therefore meaning a high temperature will be required. So why do ionic compounds have high melting and boiling points? Ions are held together by strong electrostatic forces of attraction which are difficult to overcome. Therefore, a large amount of energy is needed to break these forces. We can only get a large amount of energy by using a high temperature. This figure shows that ionic compounds can only conduct electricity when ions are free to move and carry charge. This only occurs when the ionic compound is molten or aqueous. So why can't they conduct electricity when solid? Well, the ions will be fixed in space and will be unable to carry a charge. So why can they conduct when they are liquid and molten? Well, now the ions are able to move and therefore they can carry a charge. This figure shows that ionic compounds are highly soluble in water. The charges of the ions in the ionic compound are shown here in green and yellow, which are broken apart by the water molecules. These are red and white. So why are ionic compounds soluble in water? Ionic compounds easily dissolve in water, which means that they are highly soluble. This is because both the ionic compounds and the water molecules are partially charged, or polar. Partial charges of water will break apart the ionic lattice, pulling the oppositely charged ions apart. This will cause the ionic compound to dissolve. Next, we will look at the following crystal structures as examples of macromolecules. Here is an example of a giant covalent macromolecular structure. A giant covalent structure involves lots of covalent bonds forming between several atoms which will form a giant lattice. It is a really strong structure due to having lots of covalent bonds. Each carbon atom has 4 electrons in its outermost shell. This means it can form 4 covalent bonds. This is because each of the carbon atoms needs to gain 4 more electrons to get a full outer shell. The carbon atoms have gained a full outer shell through these covalent bonds. This will form 2 macromolecular structures, graphite and diamond. We'll now look at these 2 carbon macromolecular compounds in more detail. This diamond is a giant covalent structure, as shown here. Each of the carbon atoms has formed 4 single covalent bonds with 4 other carbon atoms, as shown here, 1, 2, 3, and 4. Diamond is actually known to be the hardest naturally occurring substance found on Earth. As a result of this hardness, diamond is often used to coat drill bits. The strong covalent bonds mean that it has a very high melting and boiling point. It's a good thermal conductor due to its strong covalent bonds. Upon heating, the vibrations of the thermal energy can be rapidly transferred through the diamond. However, diamond cannot conduct electricity because the outer electrons found in each carbon atom are fixated between the atoms in covalent bonds. This means there are no free electrons that can move around and carry a charge. Diamond's insolubility is due to the attraction between the carbon atoms by the covalent bonds, which is stronger than the attraction between solvent molecules and carbon atoms. Remember, something is soluble if the attraction between the solvent and solute particles is stronger than the original bonds in the solute or solvent. Diamond is insoluble in water and organic solvents. This figure shows graphite as a giant covalent structure. It presents the covalent bonds between the carbon atoms. The carbon atoms are arranged in hexagonal sheets in layers. In graphite, each carbon shares electrons with 3 other carbon atoms, forming 3 covalent bonds. Each carbon atom has 1 outer electron that is not involved in the covalent bond. This 4th electron is said to be delocalized and is free to move around. The carbon atoms in graphite are organized into sheets of hexagons. This means graphite has a layered structure. And there are van der Waals forces in between the layers. These forces are shown by these dotted lines here. Unlike diamond, graphite is arranged in layers and sheets of carbon atoms. The layers in graphite can easily slide over each other because there are only weak intermolecular forces holding them together. Due to its slippery nature, graphite can be used in pencils and as a dry lubricant. Graphite has a high melting and boiling point. The covalent bonds in graphite are very strong, therefore a large amount of energy is needed to break them. It is also a good electrical conductor. Delocalized electrons are free to move between the sheets of carbon atoms, and therefore they can carry a charge. Here, we can see that graphite does not dissolve in any solvent. The strong covalent bonds are stronger than the attraction that would form between the solvent molecules and carbon atoms. It is insoluble in water and organic solvents. Graphite has a low density because the distance between the layers is large. As the layers in graphite are held together by only weak intermolecular forces, the layers will be found far apart. Our next specification point covers the melting point and conductivity of materials. The physical properties of a metal are determined by its bonding. These include electrical conductivity, melting point, and boiling point. Metals will have a high melting and boiling point. The melting and boiling points of a metallic compound is usually quite high because the positive metal ions are strongly attracted to the delocalized electrons. This strong electrostatic force of attraction is difficult to overcome, and a large amount of energy is required to break it, therefore needing a high temperature. As the number of delocalized electrons per metal atom increases, the melting point will also increase. This is because there is a greater electrostatic attraction between the positive ions and the delocalized electrons. Hence, the metal bond is stronger and requires more energy to break. Here, we can see that Ca2+ has got more electrons per metal atom compared to Na+. Therefore, it will have a higher melting point. There is a stronger attraction because there are more delocalized electrons and the metal ions have been more positively charged. Metals are good conductors of both heat and electricity. This is because they contain delocalized electrons which are free to move around. Delocalized electrons can carry current as well as transfer kinetic energy between themselves. Metals are insoluble in all solvents. They cannot dissolve in solvents because the metallic bonds are very strong. The exception to this rule is liquid metals. We are now going to focus on solids, liquids and gases. Solids have particles packed together closely in a regular arrangement, as shown here. In a solid, the particles are held very close together, meaning that there are a large number of particles within a fixed volume, leading to a high density. Solids are incompressible because the particles are fixed in position and therefore cannot move around. Liquids have particles arranged in a random manner and are free to move. The particles are still relatively close together. The density will be similar to that of a solid. It is only possible to compress liquids by a small extent because the particles are already quite close together. Liquids can flow because the particles are not in a fixed position. They are free to move around in solution. In gases, the particles are very far apart and free to move around. The particles will have a higher kinetic energy and can move further away from each other. Gases are usually not dense because there are only a few particles present in a fixed volume. They are also compressible because the particles are free to move around and are not held close together. Here's a summary of the different states of substances. Finally, we will look at the energy changes associated with the changes of state. In order to change the state of a substance, energy will be required. Energy needs to be put in to break the bonds and forces between the particles. Energy is used to separate the liquid particles from each other, so they move further apart. Energy will overcome the forces of attraction between the liquid particles, moving them further away and changing its state into a gas. The processes shown here in red will need heat. Those in blue need cold. Melting will go from a solid to a liquid, whilst freezing will go back from a liquid to a solid. Boiling turns a liquid into a gas, and condensation will turn a gas back into a liquid. Remember, melting or boiling a simple covalent compound does not break the covalent bonds. When you melt or boil a compound, you break the intermolecular forces between the molecules, and we are not breaking the covalent bonds between the atoms. Here, we can see the strong covalent bonds between the atoms in this molecule and the weak intermolecular forces between the two molecules. Simple covalent compounds will have low melting and boiling points. The molecules are only held together by weak intermolecular forces which require only a small amount of energy to overcome. Remember, this only applies to simple molecular compounds. When you melt or boil a giant covalent substance, the covalent bonds do need to be overcome and broken. You should learn the properties of the following main types of bonding, as you could be asked to predict the structure of a random substance based on its properties. Let's fill in the table together to show what happens. First, we'll look at ionic bonding. Our key examples for this are NaCl and NaOH. At normal temperature, these will both be solids, and they do not conduct electricity. However, as a liquid, they can conduct electricity, and they are soluble in water. Next, we'll look at simple covalent bonding.
Our examples for this are H2O and CO2. At room temperature, these are mainly liquids and gases. They do not conduct electricity as solids, and they don't conduct electricity as liquids. Their solubility in water will vary. Now, let's look at giant covalent substances. Our examples for this are graphite and diamond. These are found as solids at room temperature, and they don't conduct electricity apart from graphite, as we saw earlier. They aren't found as liquids, and they are not soluble in water. Finally, let's look at metallic bonding. Our examples for this will be copper, aluminium, and magnesium. These are found as solids at room temperature. They do conduct electricity as solids, and they will conduct electricity as liquids too. Finally, they are soluble in water. Now let's have a look at this practice question together. Pause the video now to attempt it on your own. Here, we can see that because it can only conduct electricity when molten and dissolved in solution, this applies to all ionic compounds, as when they are molten or dissolved, the ions are free to move around and carry a charge. Also, it has a high melting point. We know that ionic bonding involves a strong electrostatic attraction between the oppositely charged ions. This means a large amount of energy is needed to overcome the forces. Therefore, this unknown substance must have an ionic structure. When predicting the structure of an unknown substance, it is useful to rule out other structures. In this case, we knew that the substance could not be metallic because it only conducts electricity when molten or dissolved, so it had to be ionic. We've now covered all the learning objectives for this lesson. Feel free to skip back through the video and re-watch any of the points you are unsure about. We have now completed Lesson 4.
If you liked this video, make sure to catch our latest videos by subscribing down below and leaving a comment on a topic that you'd like to see a video on. Click here to watch more videos on our series of A-Level Chemistry, or visit our website studymind.co.uk for past paper compilations by topic and specification.